Okay, so as we indicated earlier, when we talk about motion along a curved path or motion in the plane, we're going to need a vector valued function in order to be able to think about that. We've already started talking about this a little bit when we talked about our parametric equations. The only difference now is if we want to think about the velocity and the acceleration of our object that's moving along a curved path, we need to use vectors to describe its velocity and acceleration because its motion has two components, x and y, so its velocity and acceleration have to have those same two components. So down here you can see in this formula box, we're writing our position vector in a linear combination format. Oftentimes, though, I would probably be more inclined to write this as parametric equations. So that would be, x equals some function of t, and y equals some other function of t. So I might write them as parametric equations. Or you might even see them, and usually if they do this, they write them as x of t and y of t, written either with parentheses or the angle brackets, which indicates a vector. So I'm just going to take these linear combination formulas for the acceleration and velocity vectors and write those in angle brackets. So the velocity vector with angle brackets would be x prime of t and y prime of t for position xy. And the acceleration vector would be x double prime of t and y double prime of t. And then the speed is the magnitude of the vector, of the velocity vector. So we have to take our velocity vector and do the formula for the magnitude. So that's what we'll use if we have to calculate the speed. And just like we were talking earlier, speed doesn't have a direction, so it's a scalar quantity, which is why we are using the magnitude of the vector when we talk about speed. All right, let's come down and look at example number 1. So example number 1 is going to help us to understand how we can find the velocity and acceleration vectors for a vector valued function and its speed, and we'll also start to connect how we can represent those when we graph our function in the coordinate plane. So the velocity vector, I simply have to take the derivative of the x coordinate, so that's going to be 3/2 cosine t over 2, and then I take the derivative of the y component, and so that's going to be negative 3/2 sine of t over 2. And that's my velocity vector. To do the acceleration vector, I take the derivative of each component of the velocity vector. So I derive this. That's going to be negative 3/4 sine of t divided by 2. And the derivative of the vertical component of the velocity is negative 3/4 cosine. So negative 3/4 cosine t divided by 2. And then I can actually do the speed as well. I simply need to do the square root of x prime quantity squared plus y prime quantity squared. So that's going to be 3/2 cosine t over 2 squared plus negative 3/2, move that over, the sine of t over 2 quantity squared. And that's all underneath the square root. The speed in this problem is actually rather interesting because if we rewrite this just a little bit, we're going to see that the speed is a constant. So I'm going to multiply these out. That's going to give me 9/4 times cosine squared, and I'll get 9/4 times sine squared. So we're actually going to be able to factor out a 9/4 factor, and then we'll have cosine squared t divided by 2 plus sine squared t divided by 2. This is equal to 1 using the Pythagorean identity. So this is going to be 9/4 times 1, and that's equivalent to just 3/2. So I can see that the speed is always 3/2. Now let's think about what the graph of this parametric equation would look like so we can actually see the curve and see the motion. So one way to do that would just be to pick t values and plug those in here. and pick those same t-values here and get my xy pairs and plot it out. But I'm going to do this algebraically. And we're going to use the same kind of thinking that we did over here, where we're going to have to use that Pythagorean identity. So x is, going back to the original, 3 sine of t divided by 2. And I'm going to solve that for sine. So sine of t divided by 2 is equal to x divided by 3. And I'm going to do the same thing with the cosine equation. Y is 3 cosine of t divided by 2. And I'm going to solve this for cosine. So I'll get cosine of t divided by 2 is equal to y divided by 3. Now I can take this number squared plus this number squared, and I know it's equal to 1. So sine squared t divided by 2 plus cosine squared t divided by 2 is equal to 1. And if I substitute, we're going to get x over 3 squared plus y divided by 3 squared equals 1. And when we multiply both sides of this equation by 9, we can see that this is actually a circle of radius 3. So I'm going to mark my points along the x-axis and sketch in that circle. Scaling looks a little weird on this handout. Okay. All right, it says over here to find the velocity at pi seconds and then to figure out what the answer is. So if we think about putting in pi into our position equations, the sine of pi is 0, so I know the x will be 0. And, oh, I'm sorry, we're putting pi in, it's going to be pi halves. So that'll be sine of pi halves. And so that'll be, x is going to be 3. And up here, or down here. And if I put pi in for cosine, we're going to get, also we'll get cosine of pi divided by 2, and that's 0, so the y value will be 0. So when t is equal to pi, we're going to be right here. And then I can find the velocity vector when t is equal to pi as well, and I have to come up here. So when t is equal to pi, that velocity vector is going to be 3 halves times the cosine of pi halves and negative 3 halves times the sine of pi halves. Again, the cosine of pi halves is 0, the sine of pi halves is 1, so we're going to get 0 and negative 3 halves for my velocity vector. I could draw this vector in component form and put its initial point at the origin, or I could translate that vector to anywhere I wanted, and I think it might help us to understand the problem if we translate the initial point of the vector to right here. So this vector is 0 in the horizontal direction and negative 3 halves in the vertical direction. So I can actually make it like 1.5 units long and pointing directly downward. Notice it's tangent to the curve at this point. And in fact, if I were to take and draw my point anywhere else and draw the velocity vector, it would be tangent to the curve at that point. Here's the really interesting thing. Let's put our answer over here. We got 0 and negative 3 halves. Okay. So what does this mean? That our speed is 3 halves and our position vector is, our velocity vector is 0, negative 3 halves. Well, what this means is at this point in time, we're traveling directly downward, and our speed is 3 halves. If I were to go anywhere else along this curve, and I were to calculate and plot the velocity vector, it would be tangent to the curve, and the length of that vector would always be 3 halves. The acceleration at pi seconds, I can come up and use my acceleration equation. So the acceleration at pi seconds will be negative 3/4, and then that's going to be the sine of pi halves, and then negative 3/4, and that's going to be the cosine of pi halves. And so the sine of pi halves is 1, the cosine of pi halves is 0, so this acceleration vector will be negative 3/4, 0. So right here, my acceleration vector is going to be negative 3/4, so that's to the left in the horizontal direction, and 0 which is neither up nor down in the vertical direction. And so it's only 3/4 of a unit long. So it's kind of pointing inwards on the circle. And there's your acceleration vector. Okay. All right, let's move on and try another problem. So the next problem I have is already worked out for you. So we'll talk ourselves through this particular problem. The directions on the problem say to sketch the path of an object given by this vector valued function. Remember, I and j are the unit vectors, okay? And then find the velocity and acceleration vectors and the speed at t equals 0 and t equals 2, and we want to sketch those on the diagram. So I quickly sketched this path by taking my x equation and my y equation, picking some t values that included 0 and 2, and calculating the x and y coordinates for each of those respective times. And I plotted those points. So -3, 0, -2, 1, 1, 2, and eventually over here we'd be over here at 6, 3. I didn't have room to do 13, 4 on the graph. Then I created the velocity vector and the acceleration vector. So the derivative of t squared minus 3 is 2t. The derivative of t is 1. And for the acceleration vector, you can derive the velocity vector's components. So the derivative of 2t is 2, and the derivative of 1 is 0. So calculating each of these vectors at these two different points in time, when t is 0, we'll substitute 0 for the only t, and we'll get these two vectors. And when t is 2, we'll substitute 2 for the only t, and we'll get these two vectors. Notice that the acceleration vector is the same, and that's because it's always constant. Okay? All right, let's go graph these vectors on our graph, and I'll explain how I graphed them. And then we'll do the speed, because I didn't actually include that yet. All right, so to graph this velocity vector, 0, 1, I could graph it in component form with the initial point at the origin, but it's going to be more meaningful for us if I actually position it so that the initial point is at the same place where the particle would be at t equals 0. So you can see that I went 0 in the horizontal direction and 1 unit up in the vertical direction to represent that velocity vector. So there's v. And then the acceleration vector is 2, 0, so that's 2 in the horizontal direction and 0 in the vertical direction. So right here, we have our acceleration vector. And for 4, 1, if I go to the point when t equals 2, which was 1, 2, right here, I would need to go horizontally 4 and up 1 unit. And so there's that velocity vector over 4 up 1. And my acceleration vector is the same as it was. Again, it's constant, so it's 2, 0. Wait, I should have kept my colors right. Oh well. So there's your two vectors. Here's what I'd like you to notice. The velocity vector is always going to be tangent to the path of the object, and it will be pointing in the direction of motion. So I don't know if you can see it here, but I actually indicated the direction of motion if we were plotting points as t increases from 0 on up. Let's do the speed real quick. Maybe we'll only have time to do the speed at one point. So if I want to do the speed at time t equals 0, it's simply the magnitude of this vector. So that will be the square root of 1 squared plus 0 squared, which is 1. So the speed at t equals 0 is 1. And if I wanted to do the speed at t equals 2, I need to take the components at 2, so that's going to be 16 plus 1 and square root of 17. And so at t equals 2, the speed is going to be equal to the square root of 17. You can see in the diagram that the velocity vector is a lot longer, so its magnitude should be greater. That's all we have time for. Thanks.